Okay, guys, we're going to continue on with learning about the integrated rate laws today, but we're going to do it using graphs. And then in the last part of the lesson today, we're going to talk about half-lives and how to figure out what the half-life is for these different orders. Before we start, I want to make sure you have a few things out. Number one is your Chapter 5 guided notes. You also need a calculator. I would also like to see this packet that says the integrated rate law summary. It has the integrated rate law for first order on the front page, second order, and zero order on the back page. Please have those things out. It will make what we talked about today a lot easier if you have those things ready. Okay, so let's get started. What we're going to talk about is using graphs to determine the rate law today. So I'm going to ask you to look at some plots or make some plots. And then we'll determine the rate law. So it says here that plots of A, the concentration versus time, the natural log of the concentration versus time, and 1 over the concentration versus time allow us to determine whether a reaction is going to be 0, first, or second order. So if we look at those graphs, you can quickly look at those graphs and determine whether the reaction is first, second, or zero order. Here's maybe the most important thing that I'm going to say today. Whichever plot gives you a straight line determines the order with respect to A. Say that again. Whichever plot gives you a straight line determines the order. Now, if it's linear, when you plot the concentration versus time, then it's going to be zero order. That's why there's a 0 exponent there. But if your graph is linear, when you plot natural log versus time, it'll be first order. And if it is linear, if you plot 1 over the concentration versus time, then it will be second order. I want you to take out your integrated rate law summary sheet. And let's review this for 1 second. Notice, let's go to the middle graph right here, first order. On our paper that I gave you, I put first order on the front page because they're the most common. Notice that the natural log of A versus time gives you a straight line. So if you're looking at these graphs today and you see that, and you notice that the natural log of A versus time is a straight line, that's first order. Let's go to second order. If you plot 1 over the concentration of A versus time and it's a straight line, then it's going to be second order. Let's go to zero order. If you plot the concentration of A versus time and it gives you a straight line, it's going to be zero order. So it's that simple. You just got to recognize, and they're on this paper, which one gives you a straight line. That's the one that tells you which order that reaction is. All right, so let's go through a practice problem. I'm going to go through this one with you, but there's 2 more that are going to follow that you're going to have to do on your own, so please watch. Practice problem 17. It says to complete the table and determine the rate equation for this reaction A going to 2B. So first of all, let's complete the table. What does that mean? Well, it's given us a few things here. It's given us the concentration of this reaction, of this reactant A, and it's also giving us the time values. But it's not giving us a couple of columns here, the natural log of the concentration and 1 over the concentration of A. So what we're going to do first is complete the table. How do we do that? Well, we're going to take the natural log of A at this time point. The concentration of A is 0.1. So with your calculator, you're going to do natural log of 0.1. and you get a negative 2.3. Now let's just continue on. At time point 50 seconds, our concentration was 0.067. Let's take the natural log of that. So the natural log of 0.067 is a negative 2.7. Now let's do the, for the time point at 100 seconds, the natural log of 0.05. And you get negative 3. Now we can continue on. Let's do the natural log of 0.04. And I get a negative 3.2. Natural log of 0.033. And I get a negative 3.4. Natural log of 0.029. Negative 3.5. Now let's complete this column. All we have to do is go 1 over the concentration of A. So on this first one, at time point 0, we're going to do 1 divided by 0.1. And that is 10. Let's go to the next one. 1 divided by 0.067. 14.9. Let's go to the next one. 1 divided by 0.05 is 20. The next one is 0.04, which is 25. The next one is 1 divided by 0.033, it's 30. And then finally, the last one, 0.029, gives us 35. Now, when you get those numbers filled in, how can we determine the rate equation? Well, the rate equation looks like this. Rate is equal to K times the concentration of our reactant raised to some power. So we really want to determine the order of that reaction. How do we do that? Let me show you. Notice your time values. What are they increasing by here? Is it 50 seconds every time? It is. So if you're going to make a plot or a graph this, that's 50 seconds every time interval. Now we're looking for the one that forms a straight line. Let's look at the differences between this interval. How much difference is there? 0.4. What's the difference here? 0.3. What's the difference here? 0.2. Difference here, 0.2. What's the difference here? 0.1. What's the difference here? Roughly 5, right? What's here? 5, 5, 5, and 5. Now, which one, guys, is going to give you a straight line if you were to plot it versus time? Good. I'm hoping that you're saying to yourself, this versus time will give you a straight line, won't it? If you plotted this one, this would be a curved line. The intervals are changing. But on this one, the intervals are always the same with time. That's going to give you a straight line. So, what order is it? If 1 over A versus time gives you a straight line, look at your integrated rate law summary page that I gave you. Which one plots 1 over A and gives you versus T and gives you a straight line? Second order. So we know that this is a second order reaction, so I'm going to put a little 2 right there. So there's our answer. The rate law is rate is equal to K times the concentration of A raised to the second order. Very easy, right? You just look for whichever one is going to give you a straight line. Now I've got a couple of more practice problems for you guys to try. So we noticed that the only one that gave us a straight line was 1 over a. So it's second order. All right, now I want you guys to try practice problem 18. I've already given you the values for all three of them. What I want you to do, and maybe I'll help you get started here, what's the interval changing with time?
600.
Always?
Yes.
Yes, always 600. So that's going to give you even intervals. What I want you guys to do is tell me the intervals here and notice which one is going to give you a straight line, which one is increasing or decreasing by a constant interval. So try that on your own. If you're watching the video, please hit pause now and try to figure that out. Okay, so hopefully at this point you have your intervals filled in. And let's look at it. Time is always increasing by 600 seconds. We noticed that with just the molarity, it was changing. So we stopped. It was 0.004, went down to 0.003. So if we plotted these two, it would give you a curved line because this one's changing. Then we went to the second one, the natural log of the concentration. We noticed, guys, that it's always about 0.29 difference. If we plotted that versus this, it would give us a straight line. So I think that one's our answer, but then we checked the final one. 20, 29, 30, 50. It's definitely not going to give us a straight line. So then you've got to ask yourself, which order plots the natural log of the concentration versus time and gives us a straight line? If you look at your integrated rate law sheet, the natural log of A versus time for a straight line, that's first order. So the answer here is this is a first order reaction. Okay, hopefully you got that right, and it's not too bad. I've got one more practice problem on this. So practice problem 19. Let's just try one more. Again, the time is increasing by 60 every time. What I would like you to do is look at these intervals and find out which one is going to change in a linear fashion. That's going to tell you what order this chemical reaction will be. So if you're watching the video, please hit time. Let's fill out this and determine what order this reaction is. All right, so hopefully at this point you have your answer and you've written down the intervals here. Notice if time is increasing by a constant interval, we're looking for which one increases or decreases at a constant interval. This one, which would be zero order, is definitely not constant. It's going to be a curved line if we plotted that. First order is not constant either. But when we did this for second order, we noticed that there was an interval that was consistent. That should tell you that if you plotted this versus time, it would give you a straight line. So the answer, this is second order. This reaction would follow second order kinetics. All right, how many of you guys got it right? Just curious before I solved it. Very good. That's using graphs to kind of figure out what order the chemical reaction would be. Now we're going to kind of switch gears for the last part of this lesson and talk about half-lives. Half-life is kind of self-explanatory, but here's the definition. It is the time required for 1/2 of the reactant to react. So if we start with the reactant at 1 molar, and we time it for when it is now half of that, which would be 0.5 molar, and we took that time and say it was 20 seconds, what would its half-life be? 20 seconds. It's the time it takes for half of it to react. here's the deal. For zero order reactions, the lower the initial concentration of the reactants, the shorter the half-life. Here's what I want you to recognize. This equation right here is for zero order reactions. This is how you would find the half-life. So we'd need the initial concentration of A divided by 2 times the rate constant. For first order, it's going to be different. The half-life is independent of its concentration, so we can find the half-life through this equation. And finally, for second order, it's different again. The half-life we will figure out by using that equation. Now, I don't expect that you will be able to memorize these equations. You don't have to anyway. They are on your integrated rate loss summary packet. At the very bottom, on the front page, there's the half-life for first order reactions. The very bottom of the second page is your half-life for second order, and the very bottom of the third page is your half-life for zero order. So all we're going to do is use these equations now and answer and solve for what the half-life would be. Let's do a couple examples. Practice problem number 20 says the decomposition of dinitrogen pentoxide into nitrogen dioxide and oxygen is first order. So underline that. I'm going to go through this one with you. Underline first order. It has a rate constant of 6.2 times 10 to the minus 4 per minute. That per minute is going to be important. So I underline it. It says on part A, what is a half-life? What equation should we use, guys? Zero, first, or second order equation? First order. It told us that this reaction follows first order kinetics. So let's go to our page, look up the first order page, and let's write down the equation for half-life. T to the 1/2 for first order is equal to 0.693 divided by the rate constant. So this is easy. The half-life is equal to 0.693. It told us that our rate constant was 6.2 times 10 to the minus 4. Very easy. Let's put that in our calculator and see what we get. And I'm getting that the half-life is equal to 1,117.7. But half-life is a time. We need to have units. What is the units for time here?
Minutes.
Good. It is minutes. And how do we know that? Because our rate constant K was measuring per minute. And so that's how you determine your units there.
Would not put to a -1?
Nope, it's just time. So it's 1,117.7 minutes for half of it to react. Does that make sense, guys? Very easy. Now, I'm going to give you a problem that's not so easy. I'm going to work this problem with you. Please pay attention because it will be tested. On part B, it says, what is the time required for 20%? 20% of dinitrogen pentoxide to decompose. Now, can we use the half-life equation here? No. Is that 20% is not half, is it?
No.
So if 20% reacts, that's not a half-life question. So we can't use the half-life question. Let's go back. It did tell us it was first order. Let's write the integrated rate law for a first order reaction, which says that it's the natural log of the concentration final is equal to a minus rate constant times time plus the natural log of your concentration initially. And now we kind of have to set this up in a creative way, because it didn't tell us what the final concentration should be, and it didn't come out and tell us what the initial concentration was. But it did say that 20% of it reacted. Think about that. If 20% reacts, how much do we still have? We still have 80%, right? Only 20% of it's gone. We still have 80%. So here's how I kind of work these problems. I say that the final concentration is going to be, well, actually, let me start with your initial concentration. Let's just set it up in terms of 100%. Let's say we start with 100 molar. Now, I know that's probably not what you're going to start with, but we're just going to set it up that way. So this would be the natural log of 100. What should the natural log of our concentration final be? 80, because we still have 80% left. So I'm just setting up a percentage-wise here what's going to happen. Now we've got a minus k. Our rate constant was 6.2 e to the minus 4. And we don't know time, so I'm just going to keep it as t. Now we've created a math equation with one unknown, which is t, which is what it wanted us to solve for. What I would do, because we're dealing with natural logs, is keep this in your calculator. What I would start with is natural log of 80. Then what are we going to do with the natural log of 100? Subtract it. So what I would do is hit natural log of 80 in your calculator and subtract the natural log of 100. Now, how would I get this rate constant away from the t? Divide by that. So let's divide by a negative 6.2 e to the 4th. And you should solve that t is equal to 359.9. That's what t should equal. But what are the units for time? Minutes. So you need to put minutes here. How did we know it was minutes? Again, it goes back to our rate constant was measuring per minute. Now, here's a question for you. That's right. But here's a question for you. How come it takes 1,117 minutes for half of it to decompose and only 360 minutes for 20%? Does that make sense? Do our numbers make sense? And I would say yes, this is less because we only lost 20% here. This one lost 50%. So the numbers do make sense. Okay, and we did get it right. So now what I would like you to do is I've got a couple more practice problems. Practice problem 21, I want you to try it. If you're watching the video, please hit pause at this point and try this one on your own. Okay, let's see how you did. Hopefully at this point you have your answer. Here's how I would solve this problem, okay? It says molecular iodine dissociates at 625 K with first order rate constant of 0.271 per second. What is the half-life? We're solving for half-life, and we know that it's first order. So I would get my integrated rate law summary packet out and look up first order for the half-life. The half-life equation is 0.693 divided by the rate constant. And since they told us the rate constant was 0.271, all we have to do is divide 0.693 by 0.271, and you've got your answer. So 0.693 divided by 0.271. Good. Yeah, so the answer is 2.56, but it's a half-life is a time. So what are our units going to be?
Since it's in seconds,
good. Go back to your rate constant. If it's measuring in seconds, we know that the half-life is also seconds. So t to the 1/2 here, our half-life is 2.56 seconds. How many got that right? Very good. I've got one more problem. Practice problem, and we did get that one right. Practice problem 22. Again, I would like you to try this one on your own first. So if you're watching the video, please hit pause, try it on your own. Okay, so hopefully you have solved it at this point. I would like to run through this last problem with you, make sure we've got the answer correct. It says that our reaction is Q going to 2R. So our reactant is Q. And it also said that it's second order. That's going to be important. I would underline that. Our initial concentration was 0.01. It tells us that the rate constant is 1.8. Now the wording of this question was a little different, but let's go through this last sentence here. It says, find the length of time for the final concentration to equal 1/2 the initial concentration. Another way of saying that is, what are we calculating here? The amount of time for the final concentration to equal the half of the initial. Isn't this half-life? That just means half-life. The time it takes for the concentration to decrease by half. Now, this is a second order reaction, so I would get out your integrated rate law summary page, look at the second order reactions. At the very bottom of that page, I give you the equation for half-life. It's t to the 1/2 is equal to 1 over the rate constant times A naught. Guys, what is this little 0 sign telling us? That means initial. The initial concentration. All right, now let's plug into that. So t to the 1/2 is equal to 1 over the rate constant was 1.8. Our initial concentration, they told us, was 0.01. Now be careful with your orders of operations here. I would take 1.8 and times it by 100th first. One over 0.018. Now let's do 1 divided by 0.018. And I'm getting that the half-life is equal to 55.6. But now it's very important that you get the units right. Half-life is a time. So what is our time?
Yes.
It is seconds. How do we know it's seconds?
Because it's s minus 1.
The rate constant had seconds in it. So if you were doing this reaction, you would know it would take about 55.6 seconds for it to decrease its concentration by 1/2, which is kind of interesting to know. All right, that's it for the lesson today. Before I stop the video, I wanted to give you some more practice with these types of questions. So in your student workbook, there is a worksheet titled Integrated Rate Law Worksheet. Again, it's called Integrated Rate Law Worksheet. Let's go there, get that done now, and hopefully this video helped.
What page?